The homework assignment, make sure I give that to you before you leave. And it's due tomorrow, but it really is like not that much work, trust me. And I would just review these 3 days, right? This is really only our 3rd period of this anyway, so, you know. And then we finish tomorrow, and then, you know, whatever the outline says. We test on Tuesday, I think. So, modeling data using exponential functions. We have exponential growth. An exponential function whose y values increase as the x values get larger, but not at a constant rate. So a constant rate would be a straight line. We have an exponential decay function. So growth would look like this. And decay would look like this. Okay? And we know this value here, the y-intercept, is equal to a. All right, so there's a. And there's A, and this is B. What do we know about B if it's an increasing? Greater than 1. What do we know about B? You know, because it's a short class, we don't have time. So what do we know about B if it is decay? It's between 0 and 1. Okay. So part A. Sonia did an experiment to determine the cooling curve of water. She placed the same volume of hot water in 3 identical cups. Then she recorded the temperature of the water in each cup as it cooled over time. Her data for these trials is listed in the table below. See table. Enter the data in your calculator and plot the data. Okay, this calculator's out. I need a calculator. All right, 940. Remember that. 940. Move. I don't want you there. God. 83 or 84 plus? Let's go 83. We'll go old school.
Yeah.
Okay, where's the calculator? Okay, so what you should do anytime you're putting data in the calculator, like on the exam or on diploma or wherever you're going to do more than one set, just go second plus number 4, which is clear all lists. I should move this down a bit. And then hit enter, and it'll clear all your lists out, right? If for some reason you don't have an L1, reset your calculator. Right, just the second plus 7, blah, 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 reset thing, right? And we might run through that again before the next quiz. Okay, so we're going to go to Stat, Edit. We're going to put the time, which is the independent variable, into L1. So 0, 5, 10, 20, 30, 40, and then again, 0. And then again. And we'll go over to L2, we'll put in the temps. So 80, 69, 66. We make sure things line up. Yeah, okay, so far so good. 59, 24, 32, 23, slide, and 78, 68, 61, 44, 33, 25. Okay, yeah, something's wrong. Oh, I'm missing a 5 in this list, right? So I can see something's wrong. I've got too many data items in list 2, so it means I made a mistake here. So I got to fix this. That should be 5, 10, 20, 30, 40. So one thing you want to make sure you do is double check, okay? Because you're doing this on a quiz, test, exam. It's multiple choice, numeric response on the diploma. You get one number wrong in there, your answer is wrong, right? No matter what you do, your answer is going to be wrong. So you want to double check your entries and just make sure they match up. So just take a quick slide back through 25, 33, 44, 61, 68, 78. And one way to do that is if you move over, you'll see the number in the bottom. Okay, and then 78, that should be 23, 32, 44. I'm just going backwards through the chart. 59, 66, 75, 26, 34, 45, 61, 69, 80. Okay, and 0, 5. Okay, so it's all good. Plot the data. Okay, to plot data. Well, first let's set a window. So a window, our time is going from 0 to 40. So let's go 0 to 40 for now. Do that by, I don't know, 5s, let's say. You want about 10, I like about 10 ticks on the axis. It doesn't matter, I never really look at them anyways, but you know, if you do, it's nice to have about 10 ticks maybe. And temperatures, let's say from 0 to 100 by 10s. Okay, to look at plotted data, you want to turn on the stat plot. So we go second y equals, go into stat plot, turn it on. Everything should pretty much be set. You don't need to do anything with any of the lists L1, L2. That's where we put stuff and the mark. So hit graph, and there we go. There's the data, right? It's fairly close, like 80 and 75, and whatever the other number was, 0, 78. Okay, so those points, you know, we've done 3 sets of experiments. Use the calculator to find the exponential regression function for this data, right? This unit is exponential, so we're going to do exponential stuff, of course. So stat, calc, we're looking for exp reg, which it's easier to go up and hit the bottom of the list and work your way up than to go down, right? Depending where you're at. It wasn't in the list. So exp reg. Calculators default to using L1 and L2 for the data. Okay, so we can just tell it, put the variable, so I go to vars, over to yvars, hit enter twice. So this is saying, run an exponential regression on the data in L1 and L2 and put the resulting equation into y1. And it goes and thinks about it for a while, and out pops the equation. Round values, okay, what are we supposed to do with this? Round values of the nearest to the nearest hundredth, ought the nearest hundredth. If necessary, graph this regression function along with your scatter plot. Okay, so when we write this out, okay, we're writing it in the form, so it's going to be y equals, let's say round to the nearest hundredth, I think. Yeah, so y equals 78.68, y equals 78.68 times, and the b value 0.97 to the x. Okay? So that value. So we don't write down what you see in your calculator display. You write down the actual equation. Okay? And it tells you the form, right? It's a times b to the x. Don't write that down and then say a is this and b is this. Write it out as an actual equation, right? As an exponential function. Graph this regression function along with your scatter plot. Okay, so we hit graph. There's the line. Does it fit? Looks pretty good, right? Looks like a pretty good fit. It's going through the boxes of data. Use the graph of the regression function to find the temperature of the water after 15 minutes. After 15 minutes. Okay, how do we find the temperature after 15 minutes? So go to calc, put in value. We want to put in an x value of 15, right? Because time is x values. So we go second calc value, put in a 15, hit enter, and it gives us temperature. It shows us here it is, right? Like on. And what it's doing is, that's called interpolation, right? Because it's in between data points that we've entered. So it's interpolation. And it's just finding the point on the curve. So the calculator is just looking on the curve and saying, you know, using this equation, I'm going to put a 15 in here and work this out, and this is the value you get. Okay, so 51.01 if we're going to the nearest tenth. Temperature of the water, so 51, and okay, really 51 degrees, I think is good enough. Use the equation from B to calculate this temperature of the water after 15 minutes, and then compare the two. So using this equation, we're going to go y equals 78.68 times 0.97 to the 15. Okay, so I'll quit out of the graph. 78.68 times 0.97 to the 15. Okay, and this is not the fancier calculator, which does all the nice displays. We get 49.8 degrees. 49.8 degrees. So why are they different? Shouldn't they be the same? Why aren't they the same? I see you to show. You didn't show yesterday for the test. Okay. You're right. We will. Okay. Why are these different? Why are these numbers? Why not are they the same? Yeah, because we rounded. Exactly. Right? We're using, when we wrote this down, we rounded it to the nearest hundredth. The value the calculator is using when we do that second calc value, so second calc value and put in a 15. The value the calculator is using is this exact thing, right? And that's strung out to like 10 decimal places. So yeah, they are going to be different by a little bit, right? Okay, so how do they compare? They're a little bit off due to rounding. Which one's more accurate? This, the calculator, or the equation? Calculator. Okay, so they are different. They are different due to rounding. Right? Because that thing there is rounded. So the calculator is more accurate. Gotta make an entrance. Okay, so calculator is more accurate because we rounded. Use the graph of the regression function to find the time at which the temperature of the water is 50. Okay, so how do we do that? I got my graph. How do we find what time the temperature is 50 degrees? Okay, so we go to y equals. And notice that this is the accuracy the calculator is using, right? It's like 10 or 12 decimals on there. Okay, put a 50 in for y2. Hit graph. And then what? Intersect. Yeah, so second calc intersect. I always like to just move to about the point of intersection. There. And hit enter 3 times. And we get 15.6869 minutes. 15.7 minutes, let's call it rounded. So 15.7 minutes. Now, we generally don't express time in decimals, right? You don't say how long, you don't say it takes 15.7 minutes. You say it takes 15 minutes and so many seconds. So what we want to do is convert 0.7 minutes into seconds. How do we do that? We multiply by 60 and get 42. So 0.7 minutes multiplied by 60 to turn that into seconds is 42 seconds. Okay, so 15 minutes, 42 seconds. Okay, and if I had gone more accurate than 15.7, then we would have decimal seconds, which is okay, because we do use decimal seconds, right? So if you're timing any sports event or anything like that, you know it's okay. It's 9.79 seconds or something. So we do use decimal on seconds, but we don't use it on minutes. DK. Consider the data in each table. Well, I only see one table, so consider the data in the table. Determine which data set represents an exponential growth. Well, that's going on. State the exponential. Something's missing. Oh, no, okay. There's another table on the next page. So, all right. So, part B, let's continue on the next page. Determine which data set represents growth, which represents decay. Is this table growth or decay? Growth. How do you know? Y values are getting bigger. So it's growth. Growth, which represents decay. State the exponential regression function for each. Round values to the nearest hundredth if necessary. Okay. So let's go to y equals. Let's clear out stuff that's in there. Whoops. Clear. Let's go second, lem, 4. Clear all lists. Okay. So we're going to start over. We're going to do another one. So second plus number 4, lem. So if you didn't get the last one in because you were a bit late, you can get this one in. Go to stat, edit, over to L1, 1, 2, 1, 3, 5, 7, 9. That's odd. And then the numbers that go with it, 2.03, 6.12, 14 and a quarter, 30.9, and 68.11. Okay, and then double check. Everything right? Yeah, 1, 3, 5, 7, 9, 2.03, etc., etc., etc. Okay, exponential, right? List match up in size. Stat, calc, up arrow because it's faster. X, reg. I don't know if we're doing anything with this, but vars over to y vars. Enter twice. And we are, what are we rounding to? Nearest hundredth again. So 1.498 rounds to 1.50. And what else was there? 1.54 to the x. So we have an exponential growth function, which we know since the y values are getting bigger. This reinforces that. Since the b value is greater than 1, we know that that's growth. Okay, so if you're not sure, really you can just punch it into the calculator, run the regression equation, and see what you've got there. Okay, state the round value time. State the y-intercept, the end behavior, the domain, and the range. Okay, let me bring this back. Okay, what's the y-intercept of this? One of the two letters. Y-intercept is the a value, right? So it's 1.50. A value. It's not a value, that's the a value. Whoops. I moved my frame. Come on. Cut it out. Okay, so that's the a value. What is the end behavior? What's this thing doing? What's the end behavior? There's a graph. What's the end behavior of every exponential? Quadrant 2 to quadrant 1. What's the domain of every exponential function? X is an element of the reals. What is the range? Okay, and the range is the same range of every exponential function, which is y is greater than or equal. Sorry, y is greater than 0, strictly greater than. Next table, growth or decay? Decay for so many reasons. Why is it decay? Numbers go down. The other one was growth. This one has to be decay, right? Regression equation. Okay, one more time. Stat, no, sorry, so second plus 4, clear all lists, right? Clear your lists. Doesn't hurt to go to y1 and clear it, but we'll put this on top of it anyways. Regression equation, so stat, edit. What do we got? 2, 4, 6, 8, 10, 12. Even this time. And 102.8. Oops. Really on the decimals. 44.5. 17.2. 2.7. 1.3. Okay. Get the regression equation. Stat calc. Exponential regression. Vars over to y vars. Enter twice. Put it into y1. Write it out. We're rounding to the nearest hundredth. So 250.96. Uh, 0.64 to the x. Y-intercept, 250.96. End behavior, 2 to 1. Every exponential function is 2 to 1. You know what? Let's add a little to this. Let's call this quadrant 2 to quadrant 1 decreasing. And let's go back a page and call this one, or sorry, let's go up to the top of the page and call this one quadrant 2 to quadrant 1 increasing. Right? Because that's the other characteristic of an exponential function, right? Is what's the end behavior, but what's it doing? Is it decreasing or is it increasing? What's the domain for this second one? X belongs to reals. What's the range? Okay, so standard domain, right? Now, when might that change? If it's a real life situation, like that first one we did, the domain would be that x is greater than 0. Or maybe that x is between 0 and 40 because we're timing the water cooling and we're only doing it for a certain amount of time. So our domain might be restricted. Or we might restrict it from 0 to 100 minutes. At some point that water is going to become room temperature and it's just going to stop cooling, right? It's going to get to be, so you leave a cup of coffee out, eventually it's room temperature. So, we know that happens. It doesn't take forever for that to happen. It happens often much quicker than we would like. And all of a sudden we're drinking cold coffee. So we might restrict the domain and the temperatures too, right? I mean, maybe from 100 degrees, because it's like boiling, to whatever the ambient temperature is. If we go outside, we might go from 100 degrees to minus 10 or something, right? Or minus 20 or minus 50. If we're just in a room, we may go from 100 degrees down to like 20 degrees or 15 degrees, right? And restrict the domain and range for a real life situation. Okay, here's question 3 from the textbook. 4 years ago, the Belans retired and decided to move into an apartment. Their annual rent for 4 years is given below. 9,600, 9,960, 1034, 344, and 10,752. Can this be modeled by an exponential function? So what you want to look at is the rent going up by the same amount each year? Maybe it's just a constant raise in rent. So here we say, well, that's $360. And then if we add 360 to this, we'll get, what do we get? We don't get that, right? We get a little bit lower than that. So it's not going up by the same amount. If it were a constant function, it would be a straight line. Also, this unit is called exponential regression, so it must be exponential, right? What else could it be? Yes. The increase in rent is not constant. Okay, so you could do that by saying we go up by 360, we go up by, I don't know, 344, 10, minus 9960. 384. And then 10752 minus 10344, 408. Okay, so it's increasing, but each time it increases by a larger amount. So it's probably a percentage increase then, right? Without using exponential regression, approximately what is the annual rate of increase in rent? Okay, so what's the percent increase then? So what is 360 as a percentage of 9,600? How would we figure that out? So you take 360 out of, just like you're trying to figure out your percent on a test, right? You take your mark out of the total, multiply by 100, and that gives you the percent. So we take 360 of 9,600 times 100 is 3.75. What about 384 divided by 9960 times 100? 3.85. What about 408 divided by 10344? 3.94. So what's the percent increase, approximately? Okay, so 360 divided by 9,600 times 100 was 3.75%. What do we do? 384 divided by 9960 times 100 was 3.85%. And the last one was 408 divided by 10344, which was 3.94%. Okay, so times 100. So if I were saying, what is it about it? It's around 4%. Right? You're getting around a 4% increase in rent. Calculate the exponential regression function. Round the values to the nearest hundredth if necessary. Okay, so second, mem, clear all lists. Go to stat, edit. We're going 0, 1, 2, 3. 0, 1, 2, 3. Enter and over, and we've got 9,600, 9960, 10344, 10572. Stat, calc, up to x reg, vars over to y vars, stick it into y1. So 9627.89. Get that right? 0, 1, 2, 3, 967. Oh, 10752. 10752. Didn't I say check your numbers? Aren't you checking my numbers? Nobody could say anything? Sheesh. All right, let's try that again. Okay, did you get this? The one of you that's doing it, sorry, the two of you that are actually following along and punching this into your calculator. You know, if you don't follow along and do it in your calculator, when you hit that test and you haven't done any homework either, you're going to be sitting there going, I know I've seen this done, but I don't have any actual practice in doing it, and you won't be able to do it on a test. If you follow every example in class, even then if you just don't do enough homework, you've at least done 4 or 5 in class, you have a fighting chance on a test to be able to pick up a calculator and do this and remember where stuff is. So it's up to you. I mean, I'm not going to sit there and grab you by the hand and punch the buttons for you. You do it or you don't. But the more practice you get in doing this, the easier it is to do when it's crunch time and you have to do it. Okay? Anyway, so what do we got? Y equals 9595.43. 9595.43 times 1.04, so we're rounding, right? 1.04 to the x. Is the b value close to or the same as what you calculated above? So we have three different b values, right? 3.75, 3.85, 3.94. This b value of 1.04, okay, b is greater than 1, so we know it's increasing. The rate of increase, to find the rate of increase, you actually take the b value, you subtract 1 from it, giving you 0.04, multiply that by 100 and change it into 4%. So this is a rate of increase of 4%. Right? It's like if you're going to the store and you're trying to figure out, what am I going to pay for this item? You take the price, multiply it by 1.05, which adds on 5%, which is the GST, and then you know, okay, when I go to the register, this is how much money I have to have, right? Unless there's pennies in there and you're paying cash, and then you round to the nearest 5, unless on the pennies. So, but that's how you figure out a rate of increase. What rate is this increasing? You take 1.04 minus 1 is 0.04. That's as a decimal. Turn it into a percent by multiplying by 100. And what we have is a 4% increase. Okay? So when you're looking at a b value, subtract 1, multiply by 100, that's the percent increase. When you're looking at a b value that is less than 0, so let's say we had a b value of 0.8, nice 8, 0.86. What's the rate of decrease then? Is it 86%?
Yeah.
Think about what's the rate of decrease? If your b value was 0.86, what would your rate of decrease be? Let's change it up. Let's make it a bit easier. Say it was 0. Wow, lots of stuff there. Say it was 0.75. It was 0.75. How much was the decrease? What's it decreasing by? 0.25. Right? So the way you think about this, if you have a b value less than 1, you like 0.75, you go 1 minus 0.75, which is 0.25. And then you multiply that by 100, and that's 25%. So if the b value is 0.75, your decrease is 25%. Think about it this way. If you walk into the store and it says 25% off, and you want to calculate what you're going to pay, the item's $100, you could say, okay, it's $100 and I save 25%, which is $25. 100 minus 25 is 75. Or you could say, since it's 25% off, I'm going to pay 75% of the original price. And 100 times 0.75 gives me the 75. And that's what a b value less than 1 is, really. It's the, what's it worth now? It's worth 75% of what it was. So that 0.86 is a 14% decrease, right? Because it's maintaining, in this case, 75% of its value. With the 0.86, it would be maintaining 86% of its value, so it would be losing 14%. So that's how you can tell with a b value: increasing, subtract 1, multiply by 100, decreasing, subtract from 1, multiply by 100, and you've got a rate of decrease. What will the balloons pay in 10 years? Rounding to the nearest dollar, go back. We're going to need to graph this, or we could just look in the table, really. Right? You don't need to graph. I mean, you can just go to the table and say in 10 years, so when, here we go, 10 years, 14,001. So from table, and it says round to the nearest dollar, because it's not actually 14,001, right? Like, let's take a look. If you want to see the actual number, scroll over so you're on top of it. There's the actual number, 14,060.6384, et cetera, right? And if we keep going, what'll happen is the numbers will get over, and obviously this probably won't happen, that you'll be paying $100,000 in rent in so many years, but we gotta slow that down. It's the 3-second hold rule. All right, if it ever gets over 100,000, it can't display that many digits. We're getting close. So 60 years from now. No, never mind. If it gets over, I can't. I'd have to go to over 1 million. It can only display about 6 digits there, right? And then it'll go into scientific notation. Although at 4%. There's an interesting, never mind. Well, here's an interesting problem. Here's the problem. That was 4%, right? So here's the question for you. Let's say 1,000 years ago, you had an ancestor who gave you, oh, wait a second. Was there more to that question? Without using instruments, no, that was it. 1,000 years ago, let's say you had an ancestor who put away 1 penny for you, opened a bank account and said, 1,000 years from now, my great, whatever, granddaughter, grandson, I want them to have this money, and I'm putting away 1 penny, and it's going to get 4% interest per year. So how much money will you inherit 1,000 years later? So now it's 1,000 years later, that 1 penny has been sitting in a bank, gaining 4% interest per year. How much do you get? Take a guess. Yeah, 50 cents, $20, $100. Take a guess. 1 penny, 1,000 years ago, 4% interest per year. What's it worth now? Guess, wild guess. Come on, $1 million? Yeah, million, billion, 100,000, $27.52. $400. There. Let's do this. So we're going to take 0.01 times 1.04 to the power. All right, let's say, what's it worth in 50 years? Okay, so 50 years, it's worth 7 cents. Okay? In 100 years, it's worth 50 cents, maybe 51, depending on rounding. So in 1,000 years, what's it worth? It'll increase more each time. So it was 7 cents after 50 years. It was 50 cents after 100 years.
I'll say like
$100. Anybody else? $200, $5, $502. One more zero. Okay? Now, this is in dollars. The amount you're going to see is dollars, right? Because I put in 0.01. So a billion is 10 to the 9th. A trillion is 10 to the 12th. This is 10 to the 15th. That's $1,000 trillion. Okay? That's what that little exponential curve does. It doesn't do much in the beginning. Oh, 1 cent, 50 years, that became 7 cents. Another 50 years, it's 50 cents. Another 50 years, I mean, I don't know what if we did 150. Oh, $3.58 after 150 years, right? It's doing nothing for a long time, and then you've seen the curve, right? When it takes off, it takes off. So there's your $1,000 trillion. So don't you wish you had an ancestor 1,000 years ago? I think that's more money than there is in the world right now anyway. So.